Hi and welcome. In this video I will be talking about torque and how torque and power are correlated. I think it is important to understand these concepts because it will help you understand women. It won't help you with that, but it will help you understand bicycle gearing and power meters if you are playing with those. It will also help you understand tightening torques, torque wrenches, and engines or motors, either electric motors on electric bicycles or, God forbid, cars, or internal combustion engines like diesel and petrol engines. So all of those have a very important thing that is called torque, and this video will explain that. Before we start, I have already made a video explaining work, force, power and energy and how those are correlated, and I do suggest that you watch that video. I will make this video like an enclosed, so to speak, so you do not really have to watch that other video, but I think it might help you. So I will make that video now pop up in your top right corner, so you can click on it, watch it and then come back here. Okay, let's move on. So when we talk about a brief reminder of the previous video, there I have explained that power can be viewed as work within a certain amount of time or as a potential for converting energy from one form into another. That's what it boils down to. And here when we talk about there we talked about force as in pulling something over a certain distance, but here we will talk about torque, and torque is essentially the amount of force that we use in a sort of a circular motion. So unscrewing or screwing in, tightening bolts, that's one good example for that. And here I have drawn this. We have a nut, and let's say it is very tight and we wish to unscrew it. And for that we could use a socket wrench like this one, ratchet or whatever it's called, and use it and try to unscrew this nut. And our tool has the lever of a certain length, and I can apply a certain force on the lever. Force is measured in newtons and length is measured in meters. So if I use the force of only 1 Newton meter, and that is, if I'm on earth, the equivalent of hanging a weight that is exactly 1 kilogram of mass on the end of the lever, that is the force of 1 Newton. So if I apply that amount of force, and if this lever is 1 meter long, I will get a torque of exactly 1 Newton meter. This is the formula for torque or momentum in Newton meters equals force in newtons multiplied by this is like a distance or length of the lever, to put it really oversimplified, even though we are talking everything about vectors here. And I will not go over complicating in this video. So in meters, force multiplied by the length of our lever. So if I needed more torque than 1 Newton meter, I could make this lever be 2 meters long and apply the same amount of force at the end of it of 1 Newton. In that case I would get 1 multiplied by 2, I would get 2 Newton meters of torque. So even though I am only exerting 1 Newton of force, thanks to the length of my lever, I am getting and exerting 2 Newton meters of torque on our nut. Likewise, if I were able to exert even more force, if I were stronger, I could do with a lever that is only half a meter long and exert 2 newtons of force. In that case, I would get 2 newtons multiplied by 1/2 of a meter, 0.5, so I would again get 1 Newton meter of torque. So it is not the same as force because we have another vector in play. That's important to understand. And now what I forgot to say from the start, two things that you need to remember about torque. Now that we know, basically, I hope I've explained what it is. There is no torque without resistance. I'll explain it in the video. And power relates to torque depending on the speed that we are turning or number of revolutions per minute, or however we want to express and calculate that. So those are two important things to have in mind. And now I will first explain the first one. There is no torque without resistance. For that, I will use this tool. I get 10% of each one sold. Joking. This is a relatively strange looking torque wrench, and what it does is it allows me to set a certain torque. This is set to 4 Newton meters now, and when that torque is reached, it will start slipping. It will no longer apply the torque at the end of the tool, where I can add different kinds of adapters to screw in stuff and get the proper tightening torque but not exceed it. And now, to demonstrate how it works, this bolt is tightened pretty good, and if I insert the tool and start turning it, you can see the tool is slipping, because it will not allow me to exceed the set torque of 4 Newton meters. However, if I don't hold this tightly enough, it will keep spinning the whole setup, because there is not enough resistance for me to exert a torque that is higher than 4 Newton meters in order for the tool's safety mechanism to engage and keep slipping. So I need some sort of resistance in order to reach the torque, in order to be able to apply torque. It is similar to trying to push against something. If I'm trying to push this wall, I can exert all the force that I have. In that case, we're not talking about torque. But if it is on wheels and very light, I can relatively easily push it without being able to apply a lot of force into it, if I've explained properly. So another example is with this bolt that is loose. I can start screwing it in, and it goes easily. I can do it like this, and then it starts going harder. So now I have to use this wider section to give me a better leverage so I can use the tool. And it's tightening, tightening, tightening. And now we've reached the 4 Newton meters, and it will not allow me to provide to apply any stronger torque than 4 Newton meters. So the limits, as we can see, one limit of torque is my strength. If I don't use a good enough lever, I cannot apply too much torque. So that is one limit. And the other limit is the resistance. And that is important. For example, if you need to start on a steep incline, either with a bicycle or a car, if the ground is slippery, you will not be able to start very efficiently, because no matter how much torque you are able potentially to provide, the wheel's traction is the weak link, and the ground will not provide you with enough resistance to apply that torque. So you'll be just going in, spinning in the air, like with no resistance, like you're slipping. And the same thing happens in any other similar situation. So those are some limits that we need to have in mind when we talk about torque. Similar thing happens for braking. There you're also applying torque, but only in reverse. And if you press your brakes too suddenly and too hardly, the wheel will lock, and it will no longer have any resistance. It will have highly reduced traction, and it will start skidding and sliding, and then your braking torque or braking power, that term is often used, will be greatly reduced. That is what ABS systems do on cars and some motorcycles. They release the brake when they notice that there's no more torque being applied, that the wheel is sliding, in order for the wheel to regain traction, and so that they can reapply the brake then quickly, and hopefully the driver will remove the pressure from the braking pedal when they notice that the ABS is working, because they are losing traction and not getting the maximum amount of braking torque in this case. So those are the principles: the strength and power that we have when we are trying to apply it, and the amount of resistance. Okay, I hope I've explained this properly. Now I'll just briefly talk about the relation of power and torque. We said in the before mentioned video that we measure and express power in watts, among other units. And we can say, when we talk about torque, that power equals the amount of torque applied multiplied by the angular speed, or angular velocity, I think is the proper English term, and it is measured and expressed in radians per second. One whole circle of 360 degrees has exactly 2 pi radians. I mean the number pi, that roughly equals 3.14 something. No idea how it goes on, have to Google it. So the one 360 degree turn is 2 pi radians. And we often see power and torque expressed as power related to torque expressed in rounds per minute, RPMs, and that is what we have here. If we know that 1 minute, sorry, my bad. If we know that 1 minute is 60 seconds and one whole circle, so one whole round is 2 pi, we can calculate those, and we have 1 radian per second equals 60 divided by 2 pi RPMs, which roughly rounded up on the 2 decimals gives us 9.55 RPMs. So we could say, like in this formula, that this equals also Newton meters torque multiplied by RPMs and then divided all by 9.55, if we wish to get that number based on what we know. And how does that play out? Why is that important? I'll try to explain it and demonstrate it. If I wanted to unscrew or screw in this nut very quickly with a lot of power, I can use a small short lever and spin it very quickly. If I'm not strong enough, I would have to use a longer lever and I won't be able to spin it nearly as quickly. So we can get the same amount of power if we apply lower torque but a lot more quickly with a lot more speed, or if we apply a lot higher torque at lower speed. So increasing the speed gives us more power at the same torque. I'm not sure how to really well explain this, except again using this example. If I need to apply a certain torque, let us say that I need to apply 200 Newton meters to keep turning something using this tool, stuck bolt or whatever. I need to keep applying, say, 200 Newton meters. In order for me to keep applying 200 Newton meters of torque, I would need a lever that is about 2 meters long if my calculations are not wrong, and I'll be doing that very slowly. So I would be applying 200 Newton meters of torque, but at a very small speed, low speed, because I don't have a lot of power. However, if someone super strong came, they might be able to apply the same amount of torque, 200 Newton meters, using this lever, this short, which would probably allow them to do it a lot more quickly, unlike me doing it with a longer lever running around. So that would mean that effectively they are exerting more power. They are converting more energy from one form into another, and even though the torque is exactly the same, only because they are doing it faster, this means they have more power, or vice versa. Because they have more power, more strength, they are able to do it a lot faster. And that we can also see with when we talk about engines. That is another example that came to mind. 300, let's use horsepower instead of kilowatts for power. We usually use those for engines. If we compare a 300 horsepower truck engine, that truck engine is not able to go very fast. Even if we manage to install it into an automobile, a sports automobile, it usually has a very high capacity, very high displacement, but that's another topic. That is we won't be going in those details, but it has that amount of power. It's not able to go very fast, but it has a huge amount of torque, because that is important for trucks, because they haul stuff, heavy stuff, and they need a lot of torque for starting on an incline, or for pulling a heavy trailer or whatever. You need torque. A sports car engine, if we take a 300 horsepower sports car engine, it will not exert nearly as much torque at any moment, at any RPMs, compared to a truck's engine, but it will be able to spin very quickly and to go very fast. So it achieves its power by using very high number of RPMs, turning very quickly, without exerting a huge amount of torque at any given moment, unlike the truck engine. So those are some basic examples, and again, I'm not sure if I've managed to explain this properly, but those are some basic principles and how those things correlate, and I think that's important to grasp in order to understand any further talk about anything related to torque, from engines to tools or fasteners or similar. So that's it. Thank you very much for watching. Let me know if you have any additions or corrections in the comment section below, and I'll see you in some other video. Cheers!